Hello, and welcome to another lecture in the course. Today we're going to look at Arzelà-Ascoli, just subsection 613 in the book, and you can get the book in the link in the description. You can download a PDF or get a paperback. All right, so by the way, again, we're mostly going to be doing real analysis rather than complex analysis today, but that's what we need to do if we want to get to Montel. All right, so basically, the idea is this. If we, of Arzelà-Ascoli, at least on compact sets, that if we have pointwise bounded and equicontinuous functions, then we're going to get existence of a uniformly convergent subsequence, right? So if we have a sequence, it's bounded, just pointwise is enough, and equicontinuous, as long as we're on a compact set, we're going to get an existence of a subsequence that is uniformly convergent. All right. Now we already have a lemma about that we can, if the domain of the function was countable, we already know that we can find a subsequence, convergent subsequence. So we're going to need something about countability, right? And the thing that we get or that we're going to use is the following proposition, which is useful in many different cases. That if you have a compact metric space, then this contains a countable dense subset. Right? So there exists a countable D, which is a subset of X, such that the closure of D is everything. Now, it's not just, compact metric spaces. Lots of metric spaces have this property. C has this property. It's not compact. But in particular, compact sets have this property. All right. So let's prove this. So in this, normally, we're looking at the complex numbers. So we'll have disks, but now we're in a general metric space. So we have the ball. So the delta ball centered at X. Is all the points in capital X that are within the delta of little x. Right? That's the delta ball around X. Right? Now, because X is compact, every open cover has a finite subcover. That means that, X can be covered by the open 1 over n balls, right, for any n, right? So for any particular n, any natural number n, there exists some finite number of points, and some finite number of balls around those points of radius 1 over n, such that X is the union. So X is covered by these finitely many balls of radius 1 over n, right? So our countable set is going to be this D, which is going to be, we're just going to union over all of these n, right? And we're just going to take all those centers, right? And that's what we're going to call our D. Now, this is clearly countable because it's countable union of finite sets. So little. All right. Now let's show that it's dense. So for all little x in capital X, so for every point and every epsilon, we want to find something in D that's arbitrarily close. Well, there is an n, a natural number n, such that 1 over n is less than epsilon, and then if we take, there exists one of these centers, one of these x sub n sub j, such that that's in D, because D is all of these guys, such that x is within 1 over n ball of x sub n sub j, because, these guys cover everything, right? And that's, because 1 over n is less than epsilon, that's within the epsilon ball. So we have that the distance between x and x sub n sub j is less than epsilon. So within any epsilon, we found a point of D. Therefore, x is in D closure. All right. So D is dense, which is what we wanted to prove, right? All right. Now here's Arzelà-Ascoli, or one version of it. So this is the Arzelà-Ascoli for compact sets. So we have a compact metric space. We have a sequence of functions that are pointwise bounded, right? So for every fixed point in capital X, there's a bound, that's uniform over all the n, right? And it's equicontinuous, right? Then we get two things. So first, we get simpler. The first simpler conclusion is that this sequence is uniformly bounded. So there's a single bound that works for all the points, and furthermore that it contains a uniformly convergent subsequence, which is really the main result, right? And a lot of times, you might start off with having something that's already uniformly bounded, and you're really interested in this second conclusion, right? But well, we don't have to start with that. We can start with pointwise bounded is sufficient, right? All right. So first, we proved that if X is compact, then this sequence of functions is not just equicontinuous, but uniformly equicontinuous. Proved it last time, right? So, what does that mean? One way of writing what that means is that, it's for all epsilon, there exists a delta, right? So let's use epsilon equal to 1, right? So there exists a delta such that, for every x and for every n, right, uniformly over x and n, we have that, basically the points within delta of x go into the one ball, right? And this is one way of writing it, right? Is that if we look at the ball around centered at Fn of x of radius 1, right? And we pull that back, well, it could be more, but it's definitely going to include all of these guys. All of these guys are supposed to land in here, right? Okay. Now, there exists, again, it's compact, right? So there exists finitely many points such that X is a union of the delta balls around these finitely many points, right? And we're using this delta, right? Now, Fn is pointwise bounded, and this is finitely many points, right? So there is a single m, single bound m, such that which gives the bound at all of these finitely many points, right? X1 through xk, right? But we're never too far. The functions aren't too far. If you're still within delta, right? So if you have any point in x, it is in some delta ball, right? Around one of these guys, right? And so for all n, we have that this is true, right? Because, well, that's what this says, right? All right, so if we look at the bound for f sub n at x, we just use the inverse triangle inequality, right? We get this, and this guy is we already have a bound that's m, right? Okay, so Fn is uniformly bounded, right? Now, here is where we're going to, so now we want to prove that we have a uniformly convergent subsequence. And what we're going to do is we're going to start with a dense and countable subset, right? Then we're going to find a subsequence that works there, and then we're going to show that, well, that's good enough because every other point is sufficiently close and we're equicontinuous. So we're sort of, the values are sufficiently close, right? Well, so we have to work through that, right? All right. So as I said, because D is dense and countable, there exists a subsequence, F sub n sub j, that converges pointwise on D. So it doesn't, we don't know if it converges anywhere else, but it converges pointwise on D, right? That's the conclusion of the result that we proved, right? That for if the domain of the function was countable, we could find a convergent subsequence, pointwise convergent subsequence, right? So that's what we have. Now, for simplicity, let's write G sub j as for f sub n sub j, just so that we we don't have to worry about this these subscripts. All right, now because f sub n is uniformly equicontinuous, G sub n is uniformly equicontinuous. It's a subset, right? It's a subsequence. So we're good. So that means that for any epsilon, there exists a delta, and we're going to use epsilon over 3 over here. But again, we're using uniform equicontinuity, right? Same exact idea. We're just using epsilon over 3 here, right? So if we're within delta, then we're getting then we're within epsilon over 3, right? The values are within epsilon over 3. All right. So this is I just rewrote from the previous slide to put it over here. All right. So now D is dense, right? So that means, no matter what this delta was, it's this x is within delta of something in D, right? That's the whole point of being dense. For any delta, that's what we have, right? Now, there exists, some centers that are in D, right? So some subset of D, finite subset of D, such that X is covered by the delta balls, right? All right. Right. So now there is an n such that for all n and m bigger than capital M, n, we have this this inequality for all L. Why do we have that? Well, because we have these guys are in D, right? And there we have convergence, right? So this is Cauchy, the Cauchy criterion, right? So, and we have finitely many, right? So I can have I can make this for all L, for all these finitely many L, right? Basically have that at the XL, these guys converge, so they're Cauchy, and then we can get a uniform capital N that works, right? So that's just the Cauchy criterion for convergence at these finitely many points. All right, so let start with any point x, and there is an L such that x sub L, the ball around the delta ball around x sub L contains x, right? Now we're using here we use the equicontinuity, right? So what does that mean? That means that That means this, right? We get that we're the functions are within the values of the functions are within epsilon over 3, right? For all j and n, right? Right. So basically, what do we have? We can compare the values of the function for different n and m, right? For different elements in the sequence at these points in D, right? And furthermore, as long as x is close to, well, the xl that we're going to be looking at, then we can, for the same function in the sequence, we can compare the values, we can bound the values also by epsilon over 3, right? And so now we put that together. So for all n and m bigger than capital N, if we look at the distance, that's really the thing that we want, the distance from the value at x of gn and gm, right? So we do, the sort of the standard estimate, right? Was triangle inequality. We add and subtract a bunch of things. We add and subtract gn at xl and then gm at xl, right? And that way we get, first we go from x to xl on the gn, right? Then we go from gn to gm at xl, and then we go with gm from xl to x, right? And we know that all three of these are bounded by epsilon over 3. So therefore, gn, the sequence, is uniformly Cauchy, right? It didn't, uniformly, we mean that it's not, we got, given epsilon, we get this n that doesn't depend on this point x, right? Right. Now, uniformly Cauchy means pointwise Cauchy in particular, right? That means that that at every point the sequence converges. So the first thing that we get is that we immediately get that Gn is actually pointwise convergent at all x, not just on D, but at all x. And then we use the uniformity, right? So it's uniformly Cauchy, therefore it's uniformly convergent, right? It's a good, if you don't know how to get that to work, it's good exercise to work out the estimate that gets you that, right? And we did use that C is complete, right, to get convergence, the pointwise convergent, right, to get a limit function to begin with, right? So we need that the target in the theorem, this thing, this thing is complete. That could be replaced by a metric space if you wanted to, but that would make the proof a little bit harder to write. So, and we only need it for complex valued things. All right. So therefore, Gn is uniformly convergent, and we're done. At least with this version of Arzelà-Ascoli. So the version that we really want is about uniform convergence on compact subsets, right? So that's not really going to be on an arbitrary metric space, but we only need it for for open subsets of C, right? So let U be an open subset of C, right? And suppose that we have this pointwise bounded equicontinuous sequence of functions, right? Then the sequence contains a subsequence that converges uniformly on compact subsets, right? Which is precisely the type of convergence that we want, right? All right. So again, a little bit of notation. Let D from Z to the boundary view be the distance to the boundary, which is the infimum of all the distances of overall, from Z to any point on the boundary, right? Now, define these sets k sub n, which are, they have to be at least 1 over n. So these points are supposed to be at least 1 over n from the boundary, and they're supposed to be, it's supposed to be a subset of u, right? So at least 1 over n from the boundary. So it's sort of, it's basically k is well away from the boundary, and we make it so that it's within the n ball, right? And we're using non-strict inequality, over here. And you can prove that Kn is compact, right? How do you prove it? Well, I mean, think about it was the topology in C, so not the subspace topology in U, but in C, and you can prove that in C, Kn is closed. If you have a convergent sequence of points, convergent in C of points in Kn, now, well, you can prove that these inequalities are going to be preserved. You're gonna suddenly be closer to the boundary than 1 over n if they're all less than all of these points are further away from the boundary than 1 over n, right? And same thing was less than or equal to n, right? So it's fairly easy to see that it is closed. It's also bounded. That's this second inequality, right? So it's compact. So we have compact subsets of U, right? We get that U is actually the union of all these compact subsets. So if I take, union of over all the n, right? Eventually, every point is within some 1 over n of the boundary, right? And every point, this eventually also gets every point, right? For if we go over all n, right? So we get this union. We fill up U with compact subsets. Now, there's a little bit of an exercise to prove that the interiors. The interiors are actually given by this. You just put the strict inequality in there. It's not quite true that the opposite, that you get the closure of this thing is not necessarily this thing. You can also think about counterexamples if you want, but this way works. So the interior is open, and the interior of the next guy is going to, so k sub L is in the interior of k sub L plus 1, right? That's also fairly easy to see, right? Because, if you add to n, both of these inequalities, it becomes strict, right? And of course, that means, well, I mean, it also means from this, from this expression, right? That again, we get that U is the union of all of these. So it's covered by these open sets, right? All right, now, so we have this increasing union of compact subsets, and it covers all of U, and actually the interiors cover all of U, right? Now we can apply Arzelà-Ascoli on compact subsets, right? So we get a subsequence. We're going to call it f sub 1 comma n. So it's a subsequence of fn, and by the Arzelà-Ascoli for compact subsets, that's going to converge uniformly on K1, right? Now, we apply Arzelà-Ascoli not to Fn, we're going to apply it to F sub 1n, right? And we're going to get a subsequence of that. And you can now see why I'm why I'm writing these subsequences this way, right? But again, I don't end up with sort of this tower of subscripts out here, right? So we take in the next step we take a subsequence of F1n, and that's going to converge uniformly on K sub 2, right? And we keep going. We keep taking subsequence of subsequence of subsequence of subsequence of subsequence of subsequence, right? And it's always, the nth subsequence is gonna converge on k sub n, right? Now we're gonna do this diagonalization argument again, right? We're gonna consider this sequence, which is a subsequence of the original sequence, f sub n, right? So we're going to take the nth element of the nth subsequence. Now, any compact set K, absolutely any compact set K in U, is in some K sub L interior, right? Because these guys cover, and they're increasing, right? So you have K is covered by finitely many. Well, it's covered by the biggest one, right? So it's eventually in one of these, right? That means that it's in K sub L, right? So now what we're gonna do is we take a look at this sequence, and if you started this sequence at L, right? So if we forget the first L minus one elements, start the sequence at L. Well, that's a subsequence of the L subsequence here, right? Because we were taking subsequences of that, right? And so on, right? That means it converges uniformly on K sub L, right? Because that was the definition of, definition. That's where we applied Arzelà-Ascoli the Lth time over here, right, to get a subsequence that converged, right? So that converged uniformly on K sub L, and therefore on K, because K is a subset of K sub L, right? So all right. So some couple of exercises, right? And a couple of maybe small applications, right? And they actually have something to do with how we're gonna apply things, right? So the first one is sort of the that will have to do with our proof of Montel, which is really what we're interested in. Basically, for holomorphic functions, we don't need equicontinuity because we're going to get that the derivatives are bounded, right? Well, that's one way to prove Montel. So here is a sort of a very simple version of that. Suppose that you have a sequence of functions, and suppose that you have some uniform bound on their derivative. And we're talking here just functions on the unit interval, right? So just real functions. I mean, well, maybe complex valued, but real differentiable functions, and the derivatives are just bounded, right? I mean, you don't have to have the they can be valued in the real number. It doesn't really matter, but they're differentiable, and the derivatives are bounded, right? Bounded by some capital M, right? And for all n, right, you have the same m. So then you want to prove that there exists a subsequence that converges uniformly, and basically, you want to apply Arzelà-Ascoli, of course. I mean, that's it's an exercise in using Arzelà-Ascoli. So you want to prove equicontinuity, right? That's the point, right? So that's a sort of a typical way that equicontinuity comes up. Is actually because you have a bounded sort of uniformly, or at least locally uniformly, you have bounded derivative, right? And derivative tells you how quickly can you go somewhere else, right? How quickly can the function change? And so it tells you about the deltas and epsilon, how to get the delta from the epsilon. And so that M gives you the uniformity. All right. Now, another way, again, this is an application of Arzelà-Ascoli. If we can write things in terms of integration against functions, and again, we know that that's the way holomorphic functions work this way, right? So this is another application. So suppose that I have a sequence of functions fn, and I define, and these are uniformly bounded and continuous functions. So they're uniformly bounded on continuous functions on the boundary of the disk, so on the circle, right? That's all I'm saying, right? Then suppose that g is a single function that is actually continuous. It's a function of two complex variables. It's defined on not for all z and w, but it's defined for z in the closed unit disk, right? And w are in the boundary, right? So that's a nice compact set, and we're saying that g is this continuous function on this compact set, and we define f sub n as integration of little f's against this g on the boundary, right? So we integrate, we use z, we just plug that in, and w is the thing on the boundary, right? And so, and this, can easily see that this is actually well defined. This is not quite, we have sort of a more, this is a simpler version than what we get with holomorphic functions, but it's the kind of thing that we get with holomorphic functions, right? So we get these functions fn that are defined on the entire closed disk by basically integrating away the w around the boundary, right? So the idea is basically, again, show equicontinuity. That's the point in all of these. Show that it has a uniformly convergent subsequence, right? So these are, these two are kind of simple versions of what we're going to do, right? And simple applications of Arzelà-Ascoli. There's many variations on this, right? All right. The next exercise, or the next one that I want to. There's more exercise in the book, of course, but the next one I want to emphasize here. I suppose that you have a compact metric space and an equicontinuous sequence of functions, and suppose that it converges pointwise. Then show that it converges uniformly, right? So if I have an equicontinuous sequence of functions that converges pointwise on a compact metric space, then it converges uniformly, right? All right. So that's good for today. And next time we're actually going to look at Montel's theorems. We're going to jump back into complex analysis and prove Montel so that we can get to the Riemann mapping theorem. All right. So, see you next time.